Hello, everyone, and welcome to this next section. I hope you all enjoyed the content that Pedro has presented to us. I personally find it was really useful, and I hope you guys have enjoyed as well. Let's start. My name is Erlon Haki. I'm a senior manager of data science and advanced analytics at CI&T. I'm a mathematician, and I research field applications for quite some time. I graduated at Universidade Estadual de Campinas, Unicamp, and I'm also an expert by Georgia Tech in the state of Georgia in the US. I'm a data enthusiast and a leading voice, at least I try to be a leading voice pushing CI&T customers through a more data-oriented practice. I'm also a Star Wars fan and speaker and enthusiast. And I've been dealing with data for quite some time, for over 6 years. And right now, data is this sort of all-powerful issue, this question that get us all involved and sometimes yield some hubris on people that really work on this field. So I really like this quote that I really would like to share with you all. We are all stardust. This is a famous Carl Sagan quote that help us understand how tiny we are compared to not only the world in itself, but also in the sea of information and data that we data scientists are challenged to analyze on our jobs. So I'm here to talk to you about machine learning and its applications, the most disruptive of them in the field right now. But this is a very hot topic nowadays. Most people use machine learning as one of those buzzwords that are flung here and there without even realizing the meaning of it. So before we start this discussion, I would like to pose this question to you all. What's machine learning anyway? And it's complicated. That's everyone that works in the field has a particular answer for this question. Most people that are not professionals working on the field use a lot of interchangeability, like machine learning, artificial intelligence, advanced analytics, it's applied data science. There's a whole range of definitions, and most of them are not quite satisfactory. For me, the main point is that we have to start with machine learning having a conscience that it's just a sub-area of what we usually refer as artificial intelligence. The same way that something might be learned in a way that is not intelligent, like if you hit a particular set of metal, it learns its shape and how it's supposed to behave. So there's learning over there, mechanical learning, but there's no intelligence attached to it. And when we talk about machine learning, this analogy is quite useful to understand what we are doing. We are providing tools so that artifact that we are working on learn something, either in an algorithmical way, either on a statistical way, either on a heuristical way. But this learning process is just a way for us to refer that artifact has the ability to converge and assume the most likely form, solution, or position that actually addresses the said challenges that we are applying it to. So in a sense, it's something that's necessary for intelligence, but that's something that without it, there's no intelligence for sure. But we can have this type of learning without actually tackling the more broader issue of machine learning. So now that we cleared it out of the way, that this is just a subset, this artifact is, for all the purpose that we're going to discuss later in this hour, all those artifacts will be programs or notebooks that have a set of characteristics, and they basically are programs and notebooks that, as that heated metal that learns how to bend and how to return to its original form, these notebooks and programs, they're able to recognize patterns in that database in order to find solutions for the problems that those notebooks were designed to solve. So there's no machine learning without a problem, without a database. Conversely, those patterns, they can be patterns in numbers, in words, in shapes. We usually think about the data in terms of structured data, but we have to have in mind that the same algorithms and notebooks can be utilized in non-structured data. So it doesn't matter if we're seeking patterns of numbers or if we're seeking patterns of distributions, colors, whatever. The point is that notebook, that program has to fit itself to find the patterns in that database, that particular data set, in that particular database. And finally, this program, they also have to represent, and in some particular times that we're going to discuss later on, they can be able to build itself when we're talking about recursive algorithms. That simple data that where patterns are searched are the data that trains that program and that notebook to take decisions and coming up with outputs that weren't precisely explicitly programmed previously in that notebook and in that particular problem. So in this very sense, the whole machine learning toolkit, the whole machine learning programs and notebooks, they're different from traditional programming where every single decision has to be previously thought and previously programmed into the algorithm and program, so a particular output can be achieved. So basically, when we're talking about machine learning is basically an umbrella that of all those techniques and tools that help those computers and using those programs and notebooks to learn and adapt on their own to that particular problem that you're trying to solve and that you modeled in that particular notebook. So once we clear this out of the way, how does it work? What would be the main techniques? What one should be concerned about? Basically, we have to be concerned about two main things. First one is data in itself. Data, the data structures, and the data sets that we're working with. There are problems where we are dealing with structured data, like a list of a set of dates, customers' IDs, products, prices, so forth, so on. This is very straightforward, a very structured set of data. So once you know that you're dealing with that data and that data is dense, you can figure out what kind of model, what kind of technique you will be using in order to create that particular set of notebooks. So you can't actually have one without the other. In order to design a particular machine learning feature that might be implemented, one always have to consider the data that we're working on and the models and techniques. We're going to discuss both of them in detail in a few minutes. But first, I just would like to point out something very unique about data and how it inflicts pressure on the models and techniques that will be ultimately implemented. Machine learning engineers and data scientists, you often come across different types of topologies for those data sets. Sometimes you have a lot of data, sometimes there's very scarce signal points, sometimes functions are continuously constant and demand certain techniques. Sometimes data just is everywhere and there's no pattern that humans at least cannot foresee and identify. So the first point is to identify what type of data is that. And before jumping into machine learning solution implementations, it's always advised to spend some time and do that old-fashioned descriptive analysis about what type of data we are working with, what type of topology we have in front of us, and ultimately have the insight about the models that we will be working. So the main point is basically that always do that traditional analysis of what's the data and what we have in hand. And once the data is set, we need to know how we're going to deal with that data in order to train those models, in order to train those algorithms and programs so they can start learning and evolving on their own. And then, as a data scientist or a machine learning engineer, one basically has to decide out of three possible options how that data will be used to train and to create a new network, a new machine learning solutions. So basically, you're facing one of those three particular decisions. Either you're going to use data in a supervised manner, or you're going to use it in an unsupervised manner, or you're going to use it on a reinforced learning manner. This is just about how you're gonna get that data that you just analyzed. You did your homework, you did your analysis about the data and its topology, and now you decide to feed that data into one of those notebooks and programs. So you have to decide how you're going to do it. Basically, what's the difference over those three techniques? First, when we're talking about supervised data training sets, basically what we're doing is that particular data set is labeled. So those programs, that artifact, the machine knows exactly what exact patterns it should look for. And basically, how we do that? Well, basically, we get that data set, we label it, and we select a small training data set to work with. And it's a smaller part of the bigger data set, but it has to be representative of the data set as a whole. So you actually have to extract that subset out of the main data, label it, and feed it to the algorithm. Well, once the algorithm is fed to with that data, that training set will basically give the algorithm an idea of how to, what kind of pattern is that in that sample set, how data points are dealt with, if some types of connections will be preferred over other types of connections. If a particular product is bought usually along with other products, well, that pair will be a privilege in the further analysis that you're going to make. So basically, you kind of give the idea of how to solve the broad problem. Also, the training data set has to be very well selected. If you train your sub data set, or if you select out of random and you end up with a biased set, there's a risk of one getting into biased ways of solving those particular problems. So this is very important when using supervised techniques. Once you start training your machine learning algorithm, you have to be sure that that training set is unbiased, is balanced, and will end up represent what that algorithm will face in a more general, and so it can actually come up with better results. Finally, if there's any kind of relationship in that training data, so those parameters and cause and effect relationships will be set, and your algorithm will be ready to go. Conversely, when you're working in unsupervised data sets, they basically have no labels. So machine will actually look for patterns at randomly. And this random association will sometimes come up with very different insights, like particular products being bought on a particular set of dates or particular days of the week, or bots if they are offered by that particular vendor or despite anybody else. So relationship between those data points are perceived by the algorithm in a way that are abstract, and there's no relationship between one or the other, like this example of a particular product and a day of the week. So instead of a specific statement, all those unsupervised learning algorithms, they will adapt dynamically over what the training data set is actually providing the information to. And finally, one can use those training data set using reinforced learning. And what is reinforced learning? Well, basically, you just, not only you don't actually have labels on it, but you also use the results of that iteration of the learning sessions that occurred previously on your data set to retrain the algorithm. So basically, those reinforcement trainings are designed in order for the algorithm to improve upon itself. This is very powerful and effective in a particular set of situations, but it's also dangerously if you're not facing a very well defined problem, because when you use reinforced learning, you're actually incurring the risk of getting more biased results than in the other two previously methods. So once you know what's supposed to happen and the problem is very well set, so then the algorithm learns by trial and error and try to come up with a better way to achieve that objective. A great example for that is algorithms that turn on and off actuator motors for robots. So you don't actually have to train your algorithm in every particular set of robots at all, but you can learn what kind of motors will be turned on and off based on how successful that machine learning algorithm is in that training data set. So it always favors reinforcements outputs, and those outputs have to be very clearly set, something that will be encouraged or discouraged depending on the problem. And well, once we cleared this, how we're going to deal with the data out of the way, basically we have to decide what type of techniques will be applied in order to come up with that particular notebook. And there are many techniques here, and this is where mathematics starts to rule. I will present to you the most commonly used and I think most studied of those techniques, starting with the artificial neural networks. And this is something that tries to emulate the human and the animal brain, basically, where there are different types of processing in that every node of that algorithm, and information is received by that node, each one of those nodes. Relations between those layers of nodes are set. And that information that a particular node processes is usually transferred to the next layer of processing through a nonlinear function. This is a very powerful and one of the most commonly used types of machine learning techniques, and I strongly encourage you all to look forward to that and get more information about. Perhaps we can discuss a little bit more on the Q&A sessions. So next, there's decision trees, mostly commonly used when we are facing problems that are not very clearly defined, and the problem is probabilistic and the problem is stochastic. So there's a chance something goes in this direction or that direction. So decision trees are very powerful techniques to implement when there's uncertainty regarding to that. Support vector machines, that's basically how one can classify information. So if you're trying to decide if that particular set of pixels belongs to a cheekbone or to a tip of finger, then you mostly will use those support vector techniques. This is just basically all the classifiers and how we deal with that. Regression analysis. This is one of the most useful and widely commonly used techniques for machine learning. And it basically carries on what we commonly use in data science of getting what would be the path that minimizes all the data points. So you don't know exactly what's going on, but that technique of setting the algorithm that will follow this pattern that minimizes the error is very commonly used in the market, and it's something that data scientists are very used and very comfortable about. And some colleagues of mine know that I like to stress out that regression analysis, without what we discussed previously, which is reinforcing learning and getting the notebook and the program to learn from its interactions. It's just regression analysis. So it's the basic thing in order to transform a regression analysis into a machine learning feature. One has to bring the learn back into the fold. Bayesian networks, which basically is the same type of idea, but applied to uncertainty and processes that are Bayesian in nature. For those of you who are not very familiar with that, it's just the type of techniques that we apply once we don't actually have the information about everything that happened. But we know that given that something happened, there's a result. So those Bayesian networks are useful when there's uncertainty, and but that uncertainty can be sometimes some way controlled or measured in ways of something that you actually. And finally, one of the most powerful ones, the GAN networks, the generative adversarial networks, which is has been very popularized lately, mostly by Google and its AlphaGo and all the other type of our Siri, Google Assistant. Those are the algorithms that actually are comprised of two different types of networks. One that actually comes up with bold ideas, and the other one that tries to counter it, trying to outsmart one another. So that's why they're called adversarial. And in that arms race, let's put it this way, both networks are trying to converge to the optimal point in that decision. All right, those are the techniques. How disruptive will those applications that we built using those techniques will be? And here I would like to share with you a rank that the prestigiously machine learning consulting Marucci Tech Labs came up last year about what would be the top 5 disruptive applications. And the criteria they used is basically 3 rulers. The first one is maturity, which is basically how technology and the data sets that are available right now are ready to hit the broader consumer markets. Let's just point out that most of the techniques and the stuff that we have discussed right now, they have been around for at least 50 years. But implementing those techniques and those pieces of software wasn't feasible because either we didn't actually have computer power, or we had smaller data sets that weren't suitable for training those programs and those algorithms. So the first criteria is maturity. How mature is that technology and that data set to hit the market? The second one is business impact. So what they realized is that those applications will be built following the money. So whenever the most impact can be caused on businesses, the several applications will be ranked from the most impactful to the least ones. And finally, what type of application will speed up and help escalate the impact of further applications? And this is something that really hits us in the heart, because it's not that this criteria privileges AI or a particular application for itself, but the point is, one application that can be broader used to spawn different other applications, that particular application will be more disruptive than any other one. So those are the three criteria that they used, and I would like to show you now. What are they? First is using those machine learning techniques to product recommendation. This is basically, we're going to discuss it a little bit further, but this is something that we have already been experiencing for the last couple of years. Every time we consume a video on YouTube or we consume a video on Netflix, especially now in this pandemic era, we are getting the result of one of those algorithms recommending a particular set of products, a particular set of recommendation. Second one is image and video recognition. And those applications are tremendous, not only for security purposes, like unlocking your cell phone screen, but also realizing where you consumers are looking at in a particular product shelf. If a car is able to drive safely on the roads, and or even if a person is in pain during a phone call, and so emergency should be called because there's a situation, there's an emergency going on. Third is closely related to that, but it's related to fraud transactions identification. And that's basically to counteract all those bad actors that are over there, to come up with different ways to defraud you and cause harm and steal and make people sometimes believe in the wrong things and do the different and not optimal course of action. So algorithms that can identify things that are not normal, things that might be fraudulent, things that are fishy and that do not fit very well with the usual behavior that customers or companies have, those algorithms will be very disruptive. And why will they be so disruptive? Because they will expand greatly what kind of trust and distrust will mean in the future. Finally, there's sentiment analysis. It's closely related to those two. But as our communication is more and more conducted through the various digital media, there's a need to make sense of how that communication is being felt, either by the people that are communicating a message or people that are receiving and responding to a certain communication. So an algorithm might be running right now and identify the silence of the audience as awe, or identify that particular silence as boredom, just because that algorithm was able to identify what kind of sentiment was expressed either in the non-structured data of your image or on the sound that you're making, or how questions were asked at the end of that presentation. And so once everything wraps up, an algorithm can say, hey, this content really engaged, people felt great about it, so it's a good speech, or no, people just fell asleep and this is not good at all. Or if a particular book was well received, or an article, if that caused positive impact or negative impact on society. So try to identify how humans might respond to content will be something that will be more and more and more important to corporations. And those machine learning applications that can correctly identify what goes on inside our minds and hearts, those particular applications will be more or less disruptive. And finally, there's a whole plethora related with that: virtual, personal, and corporate assistants. We're pretty much used to Siri and Alexa and Google Assistant as personal assistants. But as we start to become a more and more complex and digitized society, corporations will start relying on a lot of those same assistant features that we use on our very daily basis. Right now, we don't. The roles that secretaries have on corporations are very different from the roles secretaries had 10 years ago. And perhaps in a couple of years, the role of people who are who are today purchasing products will be very different, because they will use corporate assistants in order to place orders or to check if that particular invoice was correctly issued, or if the information was correctly keyed in a different set of requirements that a customer or another corporation has. Accountants might become very impacted by corporate assistance. Once everything is set, you just tell the application what type of accrual you want to do, and things can be set forth in a way that it's very different from what we're doing today. So those are the 5 disruptive applications that were identified for 2021. And I would like to deep a little bit more on them, their characteristics, their features, and the basic outcome of how they're going to interact with us. So in product recommendation, we've already discussed this, basically how we get the main products that we're consuming right now, especially in these pandemic times. We are being hit by those algorithms all the time, by Amazon, by Google, YouTube, and Netflix. But as more and more of our lives have been digitized, and the digital transformation that the pandemic brought upon us, a lot of decisions on the offline world will also be impacted by those product recommendations. Not only the type of products that will be purchased, but what kind of action should one take next? What would be the next route that a driver would take? What type of how one organizes its day? What type of provider should be recommended instead of another one based on a lot of performance skills. So product recommendation will expand tremendously, and will encompass not only products as we are experiencing right now, products and videos, but also services and service providers. And the basic features of those algorithms is that basically we're dealing with a list of recommended products that are tailor-made for consumption. Those recommendations are typically based on behavioral data. And every time we can collect data that represents a behavior, there's room for any type of those algorithms that work with product recommendation. And get this idea that products are physical items, because most of the time, more and more those things that will be recommended will be hard products, will be services, will be people, as those algorithms become more and more available. And those outcomes, right now we're seeing more traffic to different specific data in websites, that drive more engagement, drive more conversion rates, reduce churning, and ultimately end up with anything that drives behavioral data forward. When we're talking about image and video recognition, the algorithm basically are the ones that recognize and classify images, those that we discussed previously. We're talking right now about those virtual score machines that classify the type of information that we're dealing with. If a particular set of pixels denote a smile or not. So basically, what those algorithms do is they recognize and classify those images, and by doing so, all those algorithms and its kind, they end up creating more structured data out of that unstructured data. And just as, remember, right now, our computers, they are really, really good at processing those structured data. And there are more and more out-of-the-shelf algorithms to deal with structured data. But those algorithms that transform the tremendous amount of data that is unstructured and classified to structured data, the applications will just be tremendous. The basic features: object detection, face recognition, text, visual search, all types of landmarks, what type of composition. So getting information out of that unstructured data. And the outcomes that we're facing now is basically getting those videos which are broken down by frame and classified as digital images, and those digital images then get an attribute of a sense or an image or a mood. And as a result of that, richer data is generated about what happens in the real world. And that richer data will then be processed by a whole different set of algorithms, as we're going to discuss in the next one, especially fraud and things that are not what they're supposed to do. Those algorithms, though, are a little bit different. They don't rely on classification like the previous one. They rely on finding patterns. So those patterns, they actually have to match or mismatch something that has been learned through that training data, and everything that doesn't fit then is flagged as something that should be really, really looked very carefully by those who want to keep bad persons away from our lives. So those pattern recognition algorithms will start consuming all those data that might be processed by the other ones, and flag what's going on, that even if it's fishy or not. So the basic features is actually a prediction if that particular data that the algorithm is considering fits a pattern or not. If it fits, okay, it's clear to go. If it doesn't, then it's a possible malfeasance and should be looked into. The outcomes is basically protection of transactions, accounts, and conversely, authentication of valid transactions. And the whole idea is to prevent fraud. Of course, it saves a lot of money in disputes, chargebacks, insurance. So there's a huge potential for those fraud transactions algorithms to expand. When we're talking about sentiment analysis, again, this is those are classification algorithms, and those classification algorithms they have to be trained on which category that particular analysis can be related to. So when we're talking about sentiment analysis, there's a huge interface of how humans and process emotions, information, and even sometimes aspirations. The basic features is to determines what kind of outcomes might get from a presentation, as I mentioned, or from a text or whatever. And the final endpoint is to get this idea if something flies or not, if something is very well perceived, if something is engaging or not. Finally, those virtual and personal corporate assistants, we're talking about feature selection. And those feature selections, they are connected to those classification algorithms, but it has to do with what kind of implementations one has to have, what kind of things are important, what kind of things are not important, and how those assistants identify intention and ultimately end up taking the right direction and the right output that is expected of them, like setting an event on your calendar or making an appointment with your dentist. But well, those were the five most disruptive business applications. But I would like to point to you what I believe would be the most disruptive of them all. Those five are applications for business. Those are where the money and the companies are looking at. But I would like to present to you two that might be even more disruptive than those five. And this is learning. Learning how to deal with data and how to use those technologies. And this is not something related to those applications, not those techniques, but it's something that is related to us, the professionals that are working with that technology, with those technologies. So the most challenging things are how we keep our mathematical and statistical mindsets up to date, how we deal with the technological toolkit that's necessary to enable us to work on those techniques and that data, and how we can keep up with lead industry provider certifications, how much of your time you're investing in actually learning what's going on in the field, and how you keep up to date with the tendencies and things that are going on, and basically how you keep abreast. Information and techniques and new products and new features are popping out of the ground at a tremendous pace. So this challenge of learning how to deal with data and how to use those new technologies, this, in my opinion, is the most disruptive thing one could ever think about, because it has to do with ourselves, how we train and how we think about what we do, because it's no longer a matter of programming and set things up. Because not only those algorithms are being created for applications and businesses and consumers, but they are also being developed in order to facilitate and sometimes substitute the type of activities that we ourselves do as developers, as data scientists, as data engineers. And I would like to present to you how this is going to affect. That's the automated training and automated programming that most of the big clouds are developing and releasing right now. Basically, automated pipelines, full stack libraries, natural language programming. So if we don't keep up with that learning pace. Soon, those machine learning techniques that are being used on a huge database of code lines that are now online on the data providers around the world, those same algorithms will be used in order to create better, more efficient ways of developing code, of connecting pipelines, of analyzing huge sets of data and coming up with the best way to come up with a product, with an analysis, with a conclusion. And those four companies that we're talking basically about: Amazon, Databricks, Google, H2O, which I think is they're doing a tremendous work in the field. They're working with that right now. So to wrap things up, I really would like to point out to you guys that learning and keeping up with this automatic training and automatic programming is one of the most disruptive things that we as professionals should be looking after. But finally, what all those things have to do with CI&T, just to wrap up my presentation. Well, all those things that I mentioned, all those 5 top applications, and also that challenging, disruptive new ways of learning, they fit with one of the most cherished values that CI&T has. Because data right now is central to your value proposition. Right now, we are currently developing solutions for some of those business problems, particularly out of those 5 applications. We are working on most of them. We are helping to develop customers' perception of value, which means more and more companies will look after those types of solutions. And in a particular industry, if we implement a machine learning solution that yields high business impact, there's no doubt a competitor will soon want something similar, so it can all bite a little bit of that value for itself. Finally, we are building a data community. We at CI&T, we are organizing a data community, not only to share what we are doing on our different customers, but also how we communicate, how we share, how do we help each other face those choices about what type of data set am I going to use, what type of technique I'm going to implement, what kind of provocation will be presented to customers and to partners. So those applications are central in the data community. And finally, CI&T is awesome at continuous learning support, which is exemplified by what we are doing right now in the learning about things, exchanging thoughts, exchanging ideas, exchanging techniques. And so by having all those 5 pillars together, we do believe that those applications fit in what we are currently doing, and guarantee that we will be working on the edge of this tremendous disruptive revolution that's going on in the world right now. And guys, that's what I had to present to you right now, and I guess we got a little bit short of time, but if you guys have questions, I'll be more than willing to answer them.